Okay, so we haven't done enough content to fully do some of the questions that might ask in the exam, but what we can do is go over an easy example so that you hopefully get an understanding of the structure and style of both the questions and answers you're expected to give. So this is an easier question, but it's still the same type of question you'd be asked. So the question asks us to consider a language and then prove that it's either recognizable, decidable, both, or neither. So we haven't done enough to prove the fact that it's none of them. And so what we're going to do is we're just going to ignore this. So for the sake of this question, and now, we're just going to be trying to prove one of these three. Okay, so how would you prove it's one of those three? Well, let's look at the definition of recognizability, decidability, and see what we can do from there. So as mentioned earlier, a language is recognizable if there exists a Turing machine that recognizes it, and a language is decidable if there exists a Turing machine that decides it. So what that tells us is that if we want to prove a language is recognizable, what we can do is try and describe a Turing machine and explain why it recognizes it. And therefore, we will have shown that the language is recognizable because we've shown that there is a Turing machine that recognizes it. So because we're trying to show a Turing machine recognizes the language, we have to satisfy these conditions. So we'll have to show that the Turing machine accepts any string in the language and halts, and rejects or loops infinitely for strings not in the language. And similarly, if we're trying to prove a language is decidable, we have to construct a Turing machine and then explain and reason on the fact that it decides that language. So for that, you have to show that it will accept any string in the language and reject any string not in the language. So that's what we're trying to do. For this question, we'll be trying to create a Turing machine and show that it either recognizes the language, decides it, or both. So I've written all that out over here. So when you're proving decidability, recognizability, or trying to prove that it's both, you're basically going to describe slash construct a Turing machine, and at a high level, so in English words, you're just going to explain the steps the Turing machine will take to determine if the string is in the language. So you're basically describing an algorithm, or like pseudocode basically, for the Turing machine. So for decidability specifically, as mentioned earlier, you'll explain that the steps the Turing machine takes will always lead to the Turing machine giving the correct output for the string. So it will halt and accept if the string is in the language and reject if it's not. And that will be done in finite time. So when we say finite time, we just mean there's not going to be any infinite looping going on. So for recognizability, it's really similar. We need to explain that the steps the Turing machine takes will always lead to it satisfying the definition of recognizability. So if the string is in the language, we want the Turing machine to accept and halt. So we have to explain why that will be the case. And if the string is not in the language, we have to explain that the Turing machine might loop forever and never halt. And if we're trying to prove that it's both, as I said before, if a language is decidable, it's also recognizable. So to prove that it's both, you just prove it's decidable, and then at the very end, you mention the fact that because it's decidable, it's also recognizable, therefore it's both. So now we can move on to this question. So this is the language we're trying to prove recognizability or decidability on. So let's just see what it is. So it's all strings over this alphabet, where it's in this sort of form, zeros before ones, ones before twos, and twos before threes. And the number of zeros, ones, twos, and threes is the same, so it's some number k. So this would be in the language. This would also be in the language. Well, then this wouldn't, because there's a 1 before 0, which isn't allowed. And this wouldn't also, because there's more threes than other characters. So one way we could do this is like this. So just to reiterate, we're trying to find a procedure that Turing machine can take to check if the amount of zeros, ones, and twos, and threes in the input is the same. So as humans, we can just like visually count it, but for a Turing machine, the counting process will be a little different, and that's what you have to figure out in the exam. So let's say this was the input over here, 0, 0, 1, 1, 2, 2, 3, 3. So one way we could do this is to scan through the tape and then look for zeros, ones, twos, and threes as we scan along. And for each time we scan through the tape, we cross out one of each of the unique characters. And we keep doing that over and over until we have a situation where one of the characters is missing, so there's nothing left to cross out. So first, let me quickly explain the intuition behind this. So say the tape originally had these counts of the characters. So we had 5 zeros, 5 ones, 5 twos, and 5 threes. So every time we scan through the tape, we're going to remove one of each. So let's say we scan once, we'll now have 4 of each because we removed one, then 3, then 2, then 1, and eventually 0. And because they're all 0, we know that the original starting point was them being all equal because they all reached 0 at the same time. If, for example, one of them was more than the others, so let's say there were more zeros, or let's just say less zeros than all the other characters, then as we keep removing it, we'll eventually reach this situation. Then we pass through one more time, we get 0, 1, 1. And what happens here is that we have no zeros on the tape and one of each other character on the tape. And so if we detect that we've passed through the tape, and we're missing a character, but there's still other characters in the tape, that means that as we were removing it, we managed to completely remove all occurrences of one character, but there's still occurrences of other characters remaining. And so that means there were more of those characters at the start than that other character. So just to reiterate, we're going to try and pass through the tape, remove one of each character as we pass through, and keep doing this until at least one of the characters is fully removed. And once it's fully removed, we check if they were all removed. And if they were all removed, then the counts were the same, and so we accept. And if it's the case that there's still some remaining characters, when one of them is already fully removed, that means the counts were not equal, and so we reject. So for example, we start from the start. We can cross out the 0 so we can remove it. To remove a character, you can just swap it with a different one. So as we said before, Turing machines can write to the tape so they can replace characters. So we could replace this with any symbol. So let's just say a cross. So we're passing through. We cross out this one as well. Passing through, cross out the 2. Okay, now we cross out the 3. Keep going through the tape. We reach a blank symbol, which means we've reached the end of input. And so what we can tell the Turing machine to then do is go to the start and repeat this process. So cross out another 0, cross out a 1, a 2, a 3. Now we reach a blank symbol, and we're doing it all over again. So now we're trying to cross out a 0, a 1, a 2, and a 3. We keep scanning, we're looking for a 0 first, but we don't see any 0. And we also don't see any of the other characters. And so that tells us that all the characters were removed at the same time as we decremented their counts. Therefore, the original amount was equal. There were the same amount of characters. And let's say we had an extra 3 at the end. And we were scanning from the start. So we'd be looking for a 0 here. No 0. But we find a 3 when we're looking for a 0. That means all the zeros have been removed, but there's still a 3 remaining, which means there's more 3s than zeros. And so in this case, we'd reject. So that's sort of a high-level idea of what the procedure would look like, but we just need to write it down. So we'll say that we start from the beginning of tape. So go to beginning of tape. I guess that'll be step 2. Step 3 will be to, we can keep it in the same step actually. Go to beginning of tape, scan right. Remove 1, 0, 1, 1 from the tape. So we're like crossing it out. So one thing I forgot to mention. Yes, so quickly one thing. This shouldn't say remove. It should say try to remove. Because there could be a situation where we can't remove a character because we've already removed all instances of that character. So it's better to say try to remove. So the next step is to say what happens when we see a blank character. Blank character means we went through the tape and reached the end of the input section. So when we see a blank character, as we said before, if we reach the end of the input and it's the case that we couldn't remove one of the characters, or at least one of the characters, but we did remove others, that means there was a disbalance in the counts. So if during the scan, so during the pass through, we fail to remove at least one of the characters, but did remove others, so if we fail, it means they were all crossed out. So if this happened, that means the count was different. Then the amount of each unique character was different. And if that is the case, we reject. Let me just try this again. So just to reiterate, if we pass through the entire input and we found that we couldn't cross out one of the characters because all of the instances of that character were already crossed out, but we could cross out other characters, that means there were more of that other character in the input than the one we failed to cross out. In that case, we reject. Otherwise, if we could not cross out any characters, so all were already crossed out because all were, then we accept because that means all the characters got removed at the same time, and because we were removing them one at a time, the original amount was the same. Then accept, so halt and reject, accept. Otherwise, the other case is that we manage to remove one of each. Then we go back to step 2 and do the pass-through again. Okay, that's it. So just to reiterate, step 1, we scan the string, check if it's in the correct form, so zeros before ones, etc. Step 2, we go to the start of the tape, then we try to remove one of each unique character as we pass through it, and we cross it out by replacing it with an X. Then, if we reach the end of input, and it was the case that we failed to remove a character, but there were still other characters left, then that means that we reject because the original amount of characters in the tape before crossing everything out were different. The counts of unique characters, I mean. And if it is the case that we couldn't cross out any character, that means that we're all crossed out. And so we accept because that means the count was the same. On the other hand, if we crossed out one of each character, that means there might still be more stuff on the tape, and so we go back to step 2, which is where we start the scanning. And that's the entire Turing machine. So, therefore, this TM all strings in L infinite time. So when you say accept, you just say halt and accept. So I'll just quickly rewrite this one. So same for reject, so halts and rejects. So you could probably elaborate more on each of these sections and explain why your conclusions are correct, but that would be a bit too verbose. And so we're just going to say that by construction, we have created a Turing machine. So we create a Turing machine that decides L. So therefore, L is Turing decidable. So you should write that out properly, but I'm just not doing that for the sake of saving time. So at the end, you have to do this final step where you say that the Turing machine decides L, and therefore L is Turing decidable. And don't forget to talk about this finite time thing. It's very important. Always mention finite time, and that it'll always halt for decidability specifically. Okay, that's it for this question. If something wasn't clear, just let me know.